coupled first order differential equations. These are kind of simultaneous differential equations. Can I just point out, because these questions tend to be quite long, my handwriting is very bad, I'm just going to talk over a completed version of a pack. So an example of a pair of coupled first order differential equations is shown here. dx by dt is x plus 4y, dy by dt is 2x plus 3y. So these should be viewed in the following way. X and y are variables which are both functions of t. We can think of t as being time. The rate of change of x is dependent upon the values of x and y according to the first differential equation. dx by dt is x plus 4y. And the rate of change of y is dependent upon the values of x and y depending on the second differential equation. dx by dy by dt is 2x plus 3y. Solving these means to try to find an expression for x in terms of t and an expression for y in terms of t. Now, what I'm going to show you is that any pair of coupled first order differential equations of this form can be converted into a second order differential equation involving two variables, either a second order differential equation linking x and t or a second order differential equation linking y and t. Now, I think a question of this type is highly likely to be a show that question. I'm going to show you how to convert these differential equations into this second order differential equation with y's and t's in it. d2y by dt squared minus 4dy dt minus 5y is 0. Now, this is done in 3 steps. Because we want to get a second order differential equation with dy by dt in it, we start with the second of our given differential equations. I'm going to call them 1 and 2. So I'm going to start with equation 2 because that's got dy by dt in it, and I'm going to differentiate that equation with respect to t. So if you differentiate dy by dt, you will get d2y by dt squared, which we want. It's in the differential equation. Equals, on the right hand side, 2 stays in front, x differentiates to give dx by dt, plus 3y will differentiate to give 3 dy by dt. That's the first step. The second step is to get rid of the dx by dt term. So I'm going to use the other differential equation, equation 1, and I'm going to substitute that in to replace dx by dt. So if you substitute in equation 1, you will get d2y by dt squared is twice in a bracket x plus 4y, because I'm replacing the dx by dt with x plus 4y plus 3 dy by dt. And that can easily be expanded to give d2y by dt squared is 2x plus 8y plus 3 dy by dt. Now, the one term I need to get rid of is this 2x terms. So the third step is to now go back to equation 2 and use equation 2 to express x in terms of y and dy by dt. So if you rearrange equation 2 to get rid of x, now you don't actually need to make x the subject of equation 2. You could just make 2x the subject, but usually you're going to want to make x the subject. So equation 2 rearranges to give x is, so take away 3y, divide by 2, x is a half dy by dt minus 3 over 2y. So I'm now going to substitute that into the line above. If you do that, you will get d2y by dt squared plus twice x, which is a half dy by dt minus 3 over 2y in a bracket, plus 8y plus 3 dy by dt. And I now have a differential equation, a second order differential equation, which only has y dy by dt and d2y by dt squared in. If you just expand the brackets on the right hand side, you will get dy by dt minus 3y, that's when times in through by 2, add 8y plus 3 dy by dt, and if you collect that and all make it equal to 0, you get the differential equation we were trying to prove. d2y by dt squared minus 4dy by dt minus 5y is 0. Now that's always going to be the first step, okay? So you start with one differential equation, differentiate it. You get rid of the other derivative by subbing in the other differential equation, and then you go back to the first differential equation to get rid of the other variable. Okay. What I now want to do is to solve this. So it says here, given that x is 3 and y is 2 when t is 0, solve these, which means find expressions for x and t and y, in terms of t. Well, I now have this second order differential equation linking y and t, which I can solve using further maths methods to get the general solution for y in terms of t. Now, second order differential equation, a number times dy by dt squared plus a number dy by dt plus a number is 0. This is solved by writing down the auxiliary equation, which is going to be m squared minus 4m minus 5 is 0. Solving that, you can factorize it or use your calculator. You could have complex roots or repeated roots or distinct roots. This happens to have distinct roots. M is 5 and m is minus 1. And then writing down the general solution for y. So y is a e to the 5t plus b e to the minus t. Now, we also need to get a solution for x. Now, what you might think you have to do is to go through the first step to write down a second order differential equation linking x and t and solve. But you don't need to do that. And if you were to do that, you would end up with too many unknown constants. Earlier, we rearranged the differential equation for dy by dt to make x the subject. So we already have an expression for x in terms of dy by dt and y. Now we know what y is, the general solution for y, we can substitute that into the previous line in order to get the general solution for x. So because x is a half dy by dt minus 3 over 2y, one little step. At some point, I'm going to have to simplify the fact, use the fact that when t is 0, y is 2. If you sub t is 0 and y is 2 into this line we've just written down here, you will get 2 is a plus b. Then, to get my solution for x, x is a half dy by dt minus 3 over 2y. So dy by dt, by straightforward differentiation, is 5a e to the 5t. Minus b e to the minus t. So times that by a half and then take away 3 over 2 lots of y. And I've marked this with a dagger symbol because I want to do something with that. If you sub in t is 0 and x is 3 into this, you will get 3 is, all of the exponential terms will give you 1 when you sub in t is 0. Half into 5a minus b, take away 3 over 2 into a plus b. That, by doing some straightforward algebra, expanding the brackets and collecting like terms, gives you 3 is a minus 2b. We now have a pair of straightforward differential simultaneous equations which we can solve for a and b. You can either subtract them to get rid of the a's or solve them on your calculator, but you will get a is 7 over 3 and b is minus a third, and therefore we now have our solution. So my expression for y is now 7 thirds e to the 5t minus a third e to the minus t. To write down my expression for x, so we have an expression for x that we've had earlier, which is x is given by all of that. We can now sub in the values of a and b and simplify to get an expression for x. So if you plug that in, that previous line, if you expand the brackets and collect like terms, gives x is a e to the 5t minus 2b e to the minus t. If you sub in a is 7 over 3 and b is minus a third, you get the solution for x. So my answer is that's the formula for y and that's the formula for x. So how you do the second part of these questions is solve the differential equation to get an expression for one of your variables, in this case y in terms of t, and then use one of the two original differential equations to get an expression for x, the other variable, in terms of t, sub in the initial values to work out unknown constants. Now, students, what I'd like to do is the following. If you turn over the page, there is a you try question. So pause the video. Give yourself 5 minutes to have a go at it. And then when you've done that, I'll go through the answer. Okay, so here's this one, folks. So this time we're asked to show a second order differential equation linking x and t. So if you number the original differential equations 1 and 2, the first thing you're going to do is differentiate equation 1. d2x by dt squared is 2dx dt plus dy by dt. Then to get rid of the dy by dt, you sub in equation 2. So that's going to give me d2x by dt squared is 2dx by dt plus x plus 2y. And then to get rid of that y, go back to equation 1 and make y the subject. So y is dx by dt minus 2x. If you plug that into the previous line, you will get d2x by dt squared plus 2dx by dt plus x plus 2 inner brackets times dx by dt minus 2x. If you expand the brackets and get it all equal to 0, the second order differential equation we were looking for comes out. Then to do the second bit, to get expressions for x and y in terms of t, given that initially when t is 0, x is 3 and y is 1. Solve this by writing down the auxiliary equation. So m squared minus 4m plus 3 is 0, has distinct roots, doesn't have to be, m is 3 and m is 1. So therefore the expression for x is e to the 3, a to the 3t plus b to the t. Obviously your a's and b's may be the other way around. It's absolutely fine. Your a will be my b and vice versa. The final solutions will be the same. Because we know when t is 0, x is 3, we get 3 is a plus b. Then to get my expression for y, I'm going to go back to this rearrangement. Y is dx by dt minus 2x and use my general solution for x to get a general solution for y. So that will give me dx by dt, which differentiating the line above is 3a e to the 3t plus b e to the t, minus 2x is minus 2a e to the 3t minus 2b e to the t. And it is sensible to collect together like terms now. So y is a e to the 3t minus b e to the t. If you sub in when t is 0, y is 1, a minus b is 1. If you solve the two simultaneous equations to get a and b by very straightforward methods, you'll get a is 2 and b is 1. And therefore, here are my solutions. X is 2e to the 3t plus e to the t. Y is 2e to the 3t minus e to the t. And we are done. Now, these types of coupled simultaneous equations can arise in real world problems, in particular in what's known as predator-prey problems. So predator-prey problems will occur when you have two species of animal, and essentially one is the predator, which eats the other one, which is the prey. And the rates of changes of the two populations of animals will be interdependent of each other. Now, here is a real-worldy kind of version of this. So a small colony of bears feed on the fish in a lake. After T years, the number of bears, B, and the number of fish, F, are modelled by these differential equations. So the rate of change of the number of bears, dB by dt, is 0.4b plus 0.1f. So what this is saying is the rate depends upon B. That's because to produce new baby bears, you need adult bears in existence to give birth to them. But it also depends upon F, because in order for the bear population to increase, they will need to feed on the fish. So first one's that. Second one, df by dt is minus 0.2b plus 0.2f. So this comes about because the more fish bears there are, the more fish that will be eaten. It'll make the population of fish go down. That's where the first term comes from. But also the more fish there are, the more baby fish that will be produced to make the fish population come up. We think it's highly unlikely that you would be expected to derive differential equations of this type. They are likely to be given to you. So we are asked to first of all show d2f by dt squared minus 0.6 df by dt plus 0.1 f is equal to 0. So if you number these equation 1 and equation 2, I'm going to start off with equation 1 and differentiate it to get d2f by dt squared. So if you do that, you will get d2f by dt squared is minus 0.2 dB by dt plus 0.2 df by dt. The next step is to rearrange the first equation, the other equation, to get rid of, don't to rearrange it, to sub in the first equation to get rid of dB by dt. So if you do that, you will get d2f by dt squared minus 0.2 bracket 0.4b plus 0.4f close brackets plus 0.2 df by dt. And if you expand the brackets, that's going to give me minus 0.08b minus 0.02f plus 0.2 df by dt. Now I need to get rid of this b here. To get rid of this b here, I'm going to go back to equation 2, the one I did earlier, and rearrange that to get b in terms of f and df by dt, because these are the quantities we are interested in. So equation 2 rearranges in the following way. If you add on 0.2b and take away df by dt, 0.2b is 0.2f minus df by dt. If you then divide through by 0.2, which is equivalent to multiplying through by 5, you will get b is f minus 5 df by dt. So that's what I'm going to replace the b in the previous line with. So this will give me d2f by dt squared is minus 0.08 times, in a bracket, f minus 5 df by dt. That's replacing b with that, minus 0.02f plus 0.2 df by dt. We're nearly there, folks, for the first part. If you expand that bracket, you will get minus 0.08f plus 0.4 df by dt. Expand in the first bracket, minus 0.02f plus 0.2 df by dt. If we then collect terms and rearrange, the differential equation does come up. So on the right-hand side, 0.4 df by dt plus 0.2 df by dt is 0.6. Bring it across, we get minus 0.6 df by dt. And then you've got a minus 0.08f minus 0.02t. If you add them together, you get minus 0.1f. Add it across and you get this. So that's part A done. Part B says initially, i.e. when t is 0, there are 4 bears. So when t is 0, b is 4. Might be worth making a note of that because we are certainly going to use that at some point. So we're going to use the fact that when t is 0, b is equal to 4, and there are 100 fish, so f is 100. I want to find expressions for b and for t, b and f in terms of t, formulas for the number of bears and the number of fish at time t. So first of all, we're going to find the number of fish by solving this differential equation. So the auxiliary equation for this differential equation is m squared minus 0.6m plus 0.1 is 0. If you solve that on your calculator, probably it turns out to have complex solutions of the form p plus or minus qi. You can rewrite the solutions as 0.3 plus or minus 0.1i. So by previous theory, because this is a differential equation linking f and t, the general solution of this differential equation is f is 0.3t brackets a cos 0.1t plus b sine 0.1t. Because we know that when t is 0, f is 100. If you replace f with 100 on the left-hand side, when t is 0, e to the 0.3t is going to be 1. A cos of 0.1t is a, because cos is 1. B sine of 0.0. So that's all right. So we already know that a is equal to 100. Then, to get my expression for f, I'm going to use the following. I know that b is f minus 5 df by dt. We wrote that down earlier, and we know that when t is 0, b is 4. Now, folks, this one gets a little bit messy. This kind of thing can happen in exams. So here is my expression for b. B is f, which is all of that thing, minus 5 times df by dt. Now, to get df by dt, I'm going to have to take that formula there and differentiate it using the product rule. So df by dt, I think I've done du by v plus v times du. So if you differentiate 0.3t e to 0.3t, you get 0.3 to 0.3t times, inside the bracket, we've got a, which is 100 cos 0.1t plus b sine 0.1t. Then u times dv is going to be 0.3t times, if you differentiate the bracket, you will get minus 0.1a, which is minus 10 0.1 times 10 sine 0.1t plus 0.1b times cos 0.1t. That's using the product rule. So it does get messy. If we sub in when t is 0, b is 4, we get this equation here. So that's just working out e to the power 0 is 0, cos of 0 is 1, sine of 0 is 0. You get 4 is 100 minus 5 brackets 30 plus 0.1b. If you do the maths, expand carefully and simplify, I think there's a slight mistake there somewhere. Anyway, you get b, maybe there isn't, that's all right. B is 108, I'm pretty sure that's what you will get from that. So what that means is we now have expressions for f and b. F is e to 0.3t into 100 cos 0.1t plus 108 sine 0.1t. B is this horrible expression here, which will simplify to give you that. Okay, folks, I'm going to stop here. Part B, we are told that initially there are 4 bears and 100 fish. So when t is 0, b is 4, and f is 100, I want to find expressions for b and f in terms of t. So if we go back to my second order differential equation, this is the one linking f and t, I can now solve this to get the general solution for f in terms of t. So if you solve this, the complementary function, sorry, the auxiliary equation is m squared minus 0.6m plus 0.1. If you solve that on your calculator, it will have complex roots of the form p plus or minus qi. The roots are m is 0.3 plus or minus 0.1i, which means here is the general solution for f, is the one that's got trig in it. E to the 0.3t brackets a cos 0.1t plus b sine 0.1t. Now, because we know there are initially 100 fish, you can substitute into that equation when t is 0, f is 100. And if you do that, on the left-hand side, you will get 100. On the right-hand side, because e to the 0 is 1, cos of 0 is 1, and sine of 0 is 0, the right-hand side just gives me a. So consequently, a is 100. Then, to get my expression for b, use this rearrangement of one of the differential equations. B is f minus 5 df by dt, along with the fact that initially when t is 0, b is 4. So this is what we are going to do is, okay. So this is what we're going to have to do with this is the following. So here is my expression for b. B is f, which is this expression here, minus 5 df by dt. Now, df by dt is a little bit of a nightmare. You're going to have to differentiate that expression there, which is a product of two things. So you need to use the product rule. So what I've done is, if u is e to the 0.3t, then du by dt is 0.3 e to 0.3t times by v, which is 100 cos 0.1t plus b sine 0.1t, plus u, which is 0.3t times dv, which is that. So I've subbed in a is 100 and differentiated inside of the bracket. Now, if you substitute into that, when t is 0, b is 4, this is what I think you should get. There's a mistake somewhere here. B is 104, not 108. Let me just change this later, boys and girls, as we go through it. So you get 4 is 100 minus 5 into 30 plus 0.1d. If you simplify that and expand the brackets, you will get that expression there. And I believe if you simplify this to get what t is, you should get b is minus 108. So if you do that, folks, that's subbing that in, there's a little mistake in this, folks, minus 108, that will give you that expression there. And consequently, we are going to end up with these formulas here. Here is my expression for f. That's replacing a with 100, b with minus 108. This ghastly expression here is my expression for t. So I've gone back to the previous line, which starts here. What I've done is I've taken out e to the minus 0.3t as a common factor. If you simplify, trust me here, you get b is e to the 0.3t brackets 4 cos 0.1t plus 104 sine 0.1t. That's by doing a little bit of non-trivial algebra. And that's part 2 of the question done. Part 3, Ask C says, using the model, how long will pass before there are no fish in the lake? So what this means is we have to solve, f is 0. So if you put the expression for f equal to 0, you get e to the 0.3t bracket 100 cos 0.1t minus 108 sine 0.1t is 0. It's factorized. The factor of e to the 0.3t cannot equal 0, so only the bracket can equal 0. 100 cos 0.1t minus 108 sine 0.1t is equal to 0. This equation rearranges to give an equation you can solve using tan. So 108 sine 0.1t is 100 cos 0.1t. Divide both sides by cos of 0.1t and then say sine over cos is tan. So tan 0.1t is 100 over 108. If you inverse tan to get 0.1t and then times by 10 to get rid of the 0.1, then in radians, you'll get t is 7.47. So what this model predicts is that the number of fish will die out after 7.47 years. Now, the final bit you're asked to do is to give a criticism of the model. And there are various criticisms that you could use, but one is related to what we have just done. We have worked out the time at which the fish population becomes 0. According to the model, after the fish population becomes 0, it will become negative, and that's impossible. So here is my solution. It projects negative amounts of fish, and also there are negative amounts of bears which can happen because you've got an exponential times the trig function, and that is impossible. Okay, folks, you may now have a go at the exercise on the next page.